Hello students, welcome to the course on Advanced Digital Communication and the course code is MCE 102. This is the course for MTech EC first semester students. Myself, Dr. Shurojit Bosak, Assistant Professor of EC Department, Guru Nanak Institute of Technology, Kolkata. And this is my official email address. Today, we are going to start lecture number 8 from the module of baseband signal receiver and probabilities of bit error. In the last class, we have completed QPSK. Now today, we are going to start coherent frequency shift keying. And the lesson objective of this topic is study various digital modulation techniques that can compute the bit error performance and compare their advantages and limitations. And the second lesson objective is study signal vector representation of various digitally modulated signals by creating signal constellation. And this topic is mapped with CO number 2 and CO number 5. So let us start lecture number 8 with the topic of coherent frequency shift keying. It is a nonlinear method of passband data transmission. Now in binary FSK or frequency shift keying, symbol 1 and symbol 0 are distinguished from each other by transmitting one of two sinusoidal waves that differ in frequency by a fixed amount. A typical pair of sinusoidal waves is described by SIT equal to square root of 2EB by TB cos 2 pi FIT, where T belongs to 0 to TB, otherwise it is 0. Now here I equal to 1 and 2 and EB is the signal energy per bit. Therefore, the transmitted frequency Fi, which is NC plus I by TB for some fixed integer NC and I equal to 1, 2. So, the symbol 1 is represented by S1T and symbol 0 is represented by S2T. So, it is a continuous phase signal in the sense that phase continuity is always maintained, including the inter-bit switching times. This form of digital modulation is an example of continuous phase frequency shift keying, that is called CPFSK. Now we observe directly that signals S1T and S2T are orthogonal but not normalized to have unit energy. We therefore deduce that most useful form for the set of orthonormal basis functions are phi it equal to square root of 2 by TB cos 2 pi FIT, where T belongs to 0 to TB and otherwise it is 0. Here I equal to 1 and 2 and correspondingly the coefficients Sij for I equal to 1, 2 and j equal to 1, 2 is defined by Sij equal to 0 to TB SIT phi JT dt. Now just putting the value of SIT and phi JT from here and SIT from here. So it now becomes 0 to TB square root of 2EB by TB cos 2 pi FIT into square root of 2 by TB cos 2 pi FJT dt. So Sij equal to square root of EB when I equal to J, and when I not equal to J, it is 0. Thus, unlike coherent BPSK, a coherent binary FSK system is characterized by having a signal space that is two-dimensional, that means n equal to 2, with two message points, that means m equal to 2. Now, which is shown here in this figure. See, M1 and M2, message point M1 and message point M2 on the two basis functions, that is phi 1 and phi 2. So S1 equal to square root of EB comma 0 and S2 equal to 0 comma square root of EB. So with the Euclidean distance between them is, this is the Euclidean distance, which is square root of TB, because you know the coordinate of M1 and M2, that is square root of EB comma 0 and 0 comma square root of EB. And the waveforms, see the S1T for the message point M1, this is, if this is the waveform, and S2T for the message point M2, this is the waveform, and they have the two different frequency, which is say F1 and F2. Now you have to calculate the error probability for binary FSKs. The observation vector X has two elements, X1 and X2, and that are defined as X1 equal to square integration of 0 to TB xt phi 1 t dt, and X2 equal to integration of 0 to TB xt phi 2 t dt, where xt is the received signal, the form of which depends on which symbol was transmitted. Given that symbol 1 was transmitted, then xt equals S1t plus Wt, where Wt is the sample function of a wide Gaussian noise process with 0 mean and power spectral density N0 by 2. If on the other hand symbol 0 was transmitted, then xt equals S2t plus Wt. Now applying the decision rule, we find that observation space is partitioned into two decision regions labeled as Z1 and Z2. So this is the decision region or decision boundary, and in this region, that is called Z1, region 1, and this region is called region Z2. So the decision boundary separating region Z1 from Z2 is the perpendicular bisector of the line joining the two message points. The receiver decides in favor of symbol 1 if received signal point represented by the observation vector X falls inside region Z1, and this occurs when X1 greater than X2, and if on the other side, if we have X1 less than X2, That means the receive signal point falls inside region Z2 and the receiver decides in favor of symbol 0. So on the decision boundary, we have x1 equal to x2. That means a random guess in favor of symbol 1 or 0. That are already discussed. So consider a new Gaussian random variable y, which is y equal to x1 minus x2. So the mean value of the random variable y depends on which binary symbol was transmitted. Given that symbol 1 was transmitted, the Gaussian random variable x1 and x2, whose values are denoted by x1 and x2, have mean values equal to square root of EB and 0. And correspondingly, the conditional mean of the random variable y, given that symbol 1 was transmitted, which is expectation of y conditional 1 equal to expectation of x1 conditional 1 minus expectation of x2 conditional 1. Now this part is 0 and this part is plus root over EB. And similarly, the conditional mean when symbol 0 is transmitted, that is expectation of y conditional 0, that is equal to expectation of x1 conditional 0 minus expectation of x2 conditional 0. So first part is 0 and second part is square root of EB. So it now becomes minus square root of EB. The variance of the random variable y is independent of which binary symbol was transmitted. Since the random variables x1 and x2 are statistically independent, so each with a variance equal to n0 by 2. So it now follows variance of y equal to variance of x1 plus variance of x2, and it now this first part is n0 by 2 and second part is also n0 by 2. So it now variance of y equal to n0. Now suppose that symbol 0 was transmitted. So the conditional PDF, conditional probability density function of the random variable y is given as f of y, y conditional 0 equal to 1 by square root of 2 pi n0 exponential minus y plus square root of EB to the power square by 2 n0. Since the condition x1 greater than x2 or equivalently y greater than 0 corresponds to the receiver making a decision in favor of symbol 1, we deduce that the conditional probability of error given that symbol 0 was transmitted. Therefore, P of 10 equal to P of y greater than 0 conditional symbol 0 was sent. So that is actually 0 integration of 0 to infinity. See the limit 0 to infinity f of y, y conditional 0 dy. So put the value of this PDF here and how to solve it. So in just y plus square root of EB by square root of 2n0. Let us assume that this part is z. Assume that y plus square root of EB by 2n square root of 2n0 equal to z. By then changing the limit of integration, we can ultimately get P10 equal to 1 by square root of pi integration of EB by 2n0 square root of TB by 2n0 into infinity e to the power minus z square into dz. So it now becomes half ERFC square root of EB by 2n0. Similarly, we may see that P01, the conditional probability of error given that symbol 1 was transmitted, has the same value as P10. Therefore, the average probability of bit error, or equivalently the bit error rate for coherent binary PSK, assuming equiprobable symbols, P equal to half ERFC square root of EB by 2n0. Okay, so this is the error probability for BFSK signal. Next, we now see the power spectra of binary FSK signal. Consider the case, or consider two transmitted frequencies F1 and F2 differ by an amount equal to the bit rate, that is 1 by TB, and their arithmetic mean equals the nominal carrier frequency, say FC, and the phase continuity is always maintained, including interbit switching times. Therefore, we may express this special case of binary FSK as follows. That is, ST equal to square root of 2EB by TB cos 2 pi FCT plus minus pi T by TB, where T belongs to 0 to TB. And using a well-known trigonometric identity, we get ST equal to square root of 2EB by TB cos plus minus pi T by TB into cos 2 pi FCT minus square root of 2EB by TB sin plus minus pi T by TB into sin 2 pi FCT. So that is square root of 2EB by TB cos pi T by TB into cos 2 pi FCT minus plus square root of 2EB by TB sin pi T by TB into sin 2 pi FCT. So here plus sign corresponds to transmitting symbol 0 and the minus sign corresponds to transmitting symbol 1. And we assume that symbol 1 and 0 in the random binary wave at the modulator input are equally likely, and that the symbols transmitted in adjacent time slot are statistically independent. Therefore, the symbol shaping function GT is defined as square root of 2EB by TB sin pi T by TB, where T belongs to 0 to TB, elsewhere it is 0. Therefore, the energy spectral density of this symbol, which is equal to psi GF equal to ATB TB cos square pi TB F by, in the denominator part, it is now pi square 4 TB square F square minus 1 whole square. So accordingly, the baseband power spectral density of binary FSK equals the sum of the power spectral densities of these two components. So it is now SBF equal to EB by 2 TB delta function F minus 1 by 2 TB plus delta function F plus 1 by 2 TB plus this term, that is the energy spectral density, that is A TB cos square pi TBF by pi square 4 TB square F square minus 1 whole square. So I am showing you the waveform, that is this is the first BPSK waveform, and this is the binary FSK waveform. See, there is an impulse at F equal to 1 by 2 TB and F equal to minus 1 by 2 TB. See, so one impulse is F equal to 1 by 2 TB, that is 0.5, another impulse is minus 0.5. So it is normalized PST SBF by 2 EB, normalized that with respect to BPSK, and normalized frequency FTB. So comparison is present for the power spectra between BPSK and BFSK. Okay, so let us stop here. Thank you, and this module is completed.